Hi, I'm John Pace, a member of the R.M. Santilli Foundation and the chairman of this World Lecture Series on Hadronic Mathematics, Mechanics, and Chemistry. It is a pleasure and honor for me to introduce you to Professor Ruggero Maria Santilli, who will present in this lecture the advanced research he did in applied mathematics when he was a member of the Center for Theoretical Physics of the Massachusetts Institute of Technology from September 1974 to August of 1977, and then a member of the Department of Mathematics of Harvard University from September 1977 to August 1981. The understanding of this lecture requires an in-depth knowledge of the various branches of Lie's theory and underlying mathematics. The lecture begins the quantitative study on the resolution of the limitations of special relativity identified in Lecture 1A. Important follow-ups are Lecture 2B on the novel isomathematics needed for the completion of the quantitative study, Lectures 3A and 3B on the needed covering of special relativity applicable within physical media, and Lecture 5A on experimental verifications and applications to cosmology. Ladies and gentlemen, it is my distinct pleasure to introduce to you Professor Santilli.
The lecture that I have prepared is not in pure mathematics, but in applied mathematics, because my intent is also to make it understandable, so I hope at least, to physicists. The next chart is, this chart is perhaps one of the most important of this series, because it identifies the various methods that we will use in our investigation, as well as the system that we intend to represent with the method themselves. And there are several. So the first one is essentially what we have called in the lecture 1A, 20th century science, which is epitomized in Lie mathematics, Lie formulations and related mathematics. Essentially, we will assume those methods are excellent, outstanding, as established in the 20th century anyhow, for the treatment of exterior dynamical problems, namely for point particles and electromagnetic waves propagating in vacuum. The first level of generalization is called Lie-Isotopic formulation and related mathematics. It is the first level of generalization of Lie theory and related mathematics, and is intended, it has been developed actually for the treatment of interior dynamical problems, namely extended particles and electromagnetic waves propagating within physical medium. However, when the systems are considered isolated from the rest of the universe, therefore verify conventional conservation law, therefore we have to use an anti-commutative algebra, and an algebra with an anti-commutative bracket, and therefore that's why Lie-Isotopic, as we will see. The next level is called the Lie-admissible formulation and related mathematics, is basically intended for the representation of open, irreversible system, which are essentially they are the most general possible system that I am aware of, that I know, for which the Lie-Isotopic methods are insufficient, as we shall see. With the passing of time and the investigation of going deeper into this problem, we were forced to include the differentiation of the preceding three levels into single-valued and multiple-valued. This means there are 6 of them. And then we were forced to introduce the isodual formulation of all 6 of them to represent antimatter. We need an anti-Hermitian mathematics to conjugate properly matter into antimatter at all levels, beginning from Newton. In conclusion, we have something like 12 different formulations, 12 different formulations, as you will see, with 12 different mathematics. And they are differentiated into first classical formulation and then their operator counterpart. This starts to give you a glimpse why we're talking about some 50 years of research by hundreds of scientists all over the world that has resulted over 30,000, an estimated number of over 30,000 pages, in which basically we will try, this series of lectures, we will try to introduce you to this complexity and the reason why you have to have this type of differentiation. Dear colleagues, let's get started. This is a picture of a typical interior dynamical system we intend to study and represent to the best of our knowledge and capability. As you can see, it depicts the Sun. But you can also think about the Jupiter, structure of Jupiter, or structure of a galaxy, any other interior dynamical system. The main assumption of this level, we are talking about level Lie-Isotopic, the main assumption is that this system is considered as being isolated from the rest of the universe. So therefore, it verifies the well-known 10 Galilean or Poincaré conservation laws. I don't have to remember, it will be offensive to the audience to remember them. But this is kind of deceptive because it gives an idea that, okay, but this can be treated with Galilean Poincaré symmetry. No way, because the interior interaction are very, as we will see, very, very, very elaborate and much dramatically more advanced than the mathematics of Galilean special relativity. First of all, let's review very briefly conceptually why we cannot treat special relativity for this type of system. Well, because special relativity is based on the equality of all physical laws for inertial reference system. Fine, this is certainly valid in vacuum. But how can I put an inertial reference system inside the Sun? Ladies and gentlemen, I'm sorry, I cannot do that. And then, of course, there is the traditional idea, okay, let's reduce the Sun to elementary particles. And the elementary particles move in vacuum, so we recover conventional theory at the level of the elementary level. Even by ignoring the no-reduction theorem of lecture 1A, how can I introduce? I have to build an extremely minute, microscopic, ultra-nano instrument to measure, to have it, and then put it in an inertial system at the particle level. It is too much. In any case, also special relativity is based on necessary absence of privileged reference frames. The only frame I can introduce for the Sun, Jupiter, or other interior system is one and one only. It is privileged, and because it is addressed with respect to the medium itself. No other frame can be meaningfully introduced. But above all, the reason why we cannot use 20th century theory, because not this particular example, but in general, the interior system that we will consider are the most general possible one. Therefore, they are opaque to light. Namely, light cannot be any longer used as the principle of causality or the construction of relativity. And that's where the point where my dear colleagues that are so attached to the special relativity, when they are exposed to a framework in which light cannot even be defined or introduced in any meaningful way, then where I have seen some anguish in my colleagues, but soon to be replaced by the interest and, of course, adopting and seeing the beauty of advancement of human knowledge. Now, those are the conceptual reasons why we cannot use 20th century mathematics. But there are other reasons. The reason is that the reason why are mathematical and not so much the physics is a consequence of the mathematics. We cannot use the mathematics underlying special relativity and quantum mechanics for the representation of those systems because the difference is just too big. Remember that Hilbert space, and they did a fantastic job for representing the structure of the hydrogen atom with an accuracy which is unbelievable, which is a tribute to Schrödinger, Heisenberg, Dirac, and so on. Those were serious scientists indeed. And the representation of this of the spectral line of the hydrogen atom is done without adulteration by throwing in parameters, throwing in arbitrary function essentially calibrated from the experimental data, and this type of manipulation are very, very frequent, have been very frequent, unfortunately, in 20th century physics. No. Heisenberg, Schrödinger, Dirac, they derive numerically exact representation of experimental data without adulteration from first axiomatic principle. It stands to the stature of those scientists. That's why they have indeed a towering place in history. So, but now you see, despite these successes, I cannot use a Hilbert space for the interior of the Sun. because it's based on the theory of linear operators on a Hilbert space. And positively, the system we are considering are non-linear. So, but in addition to that are non-local integral. This is basically the idea of a valence. Two identical electrons they couple and penetrates one inside the other, or if you want the Cooper pair, or many other system, or the synthesis of the neutron that was discussed in lecture 1A. You can see the region of overlapping, which is finite and cannot be reduced to a finite number of isolated points. Therefore, the very essence of the mathematics of the 20th century, which is the topology, is inapplicable. Because the topology is local differential, can only represent a finite number of isolated points. And this is absolutely not what we are describing. More specifically, the mathematics that we need to treat the system in which we are interested has to have an integral differential topology. And namely topology that represents this volume in which the interaction occurs. Number two, the mathematics has to represent the non-potential, non-Hamiltonian, non-linear, non interaction in a way as invariant as the 20th century theory represents in a majestic way, which is invariant, the potential interaction. I repeat the statement, because this is has to be understood in its one of the majestic beauty of the 20th century theory. We will see in lecture 2B is that they predict the same number under the same conditions at different time. This is due to the invariance of under the Galilei or the Poincaré group, as we will see, or other groups of the basic interaction, which are potential. Ladies and gentlemen, if we want to do physics of any new physics of any minimum value, and by introducing new interactions which are non-potential, we got to achieve the same result. Otherwise, our study will not resist the test of time. Will not be, at least I will not be interested. So this new interaction has to be represented in a way as invariant as the potential one, so as we predict also, under the new interaction, we predict the same numbers under the same conditions at different time, and we have indeed some physics. Finally, there is a condition for the needed mathematics which is typically physical. That's why this lecture could not possibly have been pure mathematics. It will not be, at least for me, will not be as an introductory lecture, will have missed the main point. Namely, the needed mathematics must be a covering of the mathematics of the 20th century, because this is a fundamental point that differentiates between physics and mathematics. Mathematicians, they have a degree of freedom we as physicists we don't have. They can invent completely new mathematical structure that have no connection with no pre-existing mathematics. We physicists don't have that luxury. No, because we are a chain. We cannot build new theory by ignoring Einstein. Einstein did not ignore Galilei. No, he said Galileo is recovered at low speed. Well, it's the same thing, but has to be applied to the mathematics. Well, I spent years of my life looking for the mathematics in all the library in 2 or 3 continents. Mathematics that will verify those 3 requirements. It did not exist. You reach a point in my life in which this mathematics does not exist. It's got to be built, period. And that was the beginning of this long journey. Now, by digging deeper, the biggest insufficiencies were at the level of Lie theory, because Lie is linear, local, and Hamiltonian. The system we are studying is non-linear, non-local, non-Hamiltonian, so the very essence of Lie theory was insufficient. We will see this in lecture 3A, which is a fundamental, addressing a fundamental issue of our study, which is the universal invariance of locally varying speed of light. It's known as the historically, to qualify as expert, should know, it's called as the Lorentz problem. As we will see, Lorentz was forced to reduce the invariance of this expression to a constant speed because of insufficiency. We now know because of Lie. The insufficiency was Lie. Of course, Lorentz did history, despite the simplification that is noted by Pauli, as we will see. Okay, so let's start to review this journey, this long journey of 50 years. It started at the University of Torino in Italy. I was just recently married with my wife Carla, that to whom I essentially I own everything I did, because without her help I would not have not even minutely achieved all the studies that were subsequently conducted. In Torino, I had the fortune of reading the original work by Lagrange that was mostly written in Italian. And I was shocked in reading the original Lagrange work. I was shocked of the dichotomy between Lagrange's view of nature and the physics and mathematics that was taught in the PhD courses. And namely, Lagrange's view is that there is no possibility of representing nature with one function, one quantity only. Today we call the Lagrangian, because there is the need of other forces that cannot be represented with a Lagrangian, and that's the reason why I introduced external terms in this famous analytic equation. Then I went to the Imperial College, another library in England, to study the original work of Hamilton. The followers can be studied, but with some limitation and some question in certain cases, and of course not in all cases. Hamilton is independently exactly the same view. Nature cannot be represented with the quantity we call the Hamiltonian. You need external terms. And however, already at the time of the graduate school, I recognized that the moment you add the external terms to the celebrated analytic equation, the totality of the 20th century scientific knowledge was gone, was inapplicable. It's very easy to see it because this we are talking about 40 or 50 years ago. It's easy to see because the moment you add these external forces, the bracket of the time evolution are given by this expression, and this expression now, this broader bracket, violate the conditions to characterize an algebra. In this case, right associative and scalar law. And so therefore, you lose, not only you lose the Galilean Poincaré symmetry, forget about it, you lose all the algebra. In actuality, you lose all algebra. There is no possibility of introducing an algebra. So there is no possibility whatsoever, this identified this immediately, there is no possibility whatsoever of building covering theory by using the historical Lagrange and Hamilton equation with external terms. No, because you miss an algebra, there is no, I did not even know where to start. When 10 years later I landed in Cambridge, I presented to him, being Italian, and so being naturally friendly as instinct, but of course with due correction when necessary, I presented to my colleague, as a first gesture of friendship, this vignette. This I drew it myself in the 70s. It was about 10 years later. Essentially, the vignette depicts, this executor that is chopping out the external terms in Lagrange and Hamilton's equation, and Lagrange and Hamilton yell, no, don't do it. Unfortunately, at that time I was a little bit naive. I was also much younger. I was a little bit naive. Not now. I've been educated, indeed. I know what's out there in the scientific world. It's an unregulated scientific trade, like Wall Street, totally without any regulation or inspection of any type whatsoever. That's essentially the part of the scientific process is left to the individual scientist. But anyhow, at that time, I was surprised because I saw the anguish and the extreme tension in the face of my colleagues. Then I realized that they knew what I knew, namely that the moment you add external term, Einstein relativity is gone, quantum mechanics is gone. Apparently, those colleagues were not, they don't have an interest enough to see the necessity of surpassing the 20th century theory. To paraphrase Frank Sinatra, I did it my way. Okay, let's go back to now, the objective of this lecture, to start reviewing the mathematics that is needed for the study of closed, isolated, non-Hamiltonian system. For 10 years I worked at a bigger level, which is the Lie admissible level, which is for me by far the most important. It's universal. It includes everything as particular case. So we're talking about, so I initiated quantitative studies on the Lie-Isotopic case when I finally joined the Massachusetts Institute of Technology as a member of the Center for Theoretical Physics. This was in 1974. And the objective that I decided by myself to study was that let's see the limits of representation capability by the truncated Lagrange and Hamilton equation. My dream, my hope was that if those equations can indeed represent at least some meaningful interior dynamical problem, then I have all the mathematics and the physics of the 20th century that I can use in one way or another. My job would have been much simpler. And this, the condition was obviously the so-called the conditions of variational self-adjointness, which are the necessary and sufficient condition for the existence of a Lagrangian or a Hamiltonian. This is also known as the inverse problem in Newtonian mechanics and field theory. I wrote a considerable number of papers here. I first studied, in my style, you will see this also in other cases. I'm first interested in the most general possible case, and then I specialize in sub-cases. So I first worked out the inverse problem for the most general possible tensorial field equation, and I wrote a number of articles. Here I quote 3 of them that are available in free PDF download in the Word document associated with this lecture in the web. After the series of papers on the tensorial part, I wrote 2 monographs, also at MIT, that eventually were published later on when I was at Harvard, because I needed to do historical search. Took me a year, and then I had to do additional refinement. This was pretty fancy mathematics, applied mathematics, and so that basically, so the conclusion for me to enter into technical details for this topic alone, I will need 3 semesters. 1 semester for the inverse problem in Newtonian mechanics. Indeed, I did a 1 semester seminar course when I was at Harvard after my stay at MIT, and this semester number 1. Then the semester number 2 on the covering of the inverse problem in Newtonian mechanics, that's Birkhofian mechanics, and then the 3rd semester for its formula, most general possible formulation in field theory. Ladies and gentlemen, I certainly cannot do this. I can only flash you the very, very essence, and also the results, the main results, and you scholars who are interested in learning very, very significant methods, I believe, they can study it from on their own and eventually formulate their own like seminar courses. Okay, so the starting point in everything I do is Newton. Unless I represent Newton, I don't go any further. This includes antimatter. I have to represent antimatter at the Newtonian level. This will not be today, but the spirit is the same. So let's see when Newton's equation of motion are, or the Newtonian forces can be represented with the potential. And those are the conditions of variational self-adjoint. I just write them here, you have to study them. But the people who have a geometrical inclination, they can see the beauty, for instance, of this and the connection with the symplectic. Is the very, very essence of Hamiltonian theory, Hamiltonian vacuum field, symplectic geometry, and so on. Once those conditions are verified, the calculation of the potential from Newtonian force, it's very easy. You do this integral. Sorry, maybe the word easy maybe is a little bit too much. It's possible relatively easily from via solving this integral. And the net result of this is that all Newtonian forces are divided into self-adjoint, variational self-adjoint, namely forces that are potential. Vogel said potential. They verify necessary sufficient condition to admit the potential, and the others that do not. So this chart sets the mathematical formulation of the system in which we are interested. They are variationally non-self-adjoint at the classical level, and essentially non-self-adjoint, or if you want, non-unitary at the operator level. Unless they verify those conditions, 20th century formulation apply. And ladies and gentlemen, it's magnificent work. I accept it as an editor, but personally, I have no interest whatsoever, none. Unless there is a basic novelty, I have no interest. That's at least because the beauty of the novelty of the problem that we can study is overwhelming over past knowledge, with full respect to the past knowledge. Okay, let's go to the level of equation of motions. If they're a little bit more general, then these are the more general condition of variational self-adjointness that usually those are used for a representation with a Hamiltonian. And once those are verified, then essentially everything can be calculated very easily. Indeed, they do work. Those conditions, they do work and provide actual solution with no restriction of the forces except being Newtonian. Newtonian means not to depend on the acceleration. You should keep this in mind, because later we will encounter necessarily in interior problem acceleration dependent forces. Those are non-Newtonian. And so essentially, this is the conclusion of this rather large effort. The conclusion was that there was a vindication of the legacy of Lagrange and Hamilton. Namely, dear colleagues, there are theorems in this, you can see in those books and this work. There are theorems that essentially prove that whenever you have more than one dimension, namely whenever you have an isolated particle, there's no interest. But whenever more than one particle, then Lagrange and Hamilton mechanics can only provide you a direct representation, I'll elaborate in a moment, direct representation of a potential system, a system of forces derivable from a potential. So therefore, the conclusion of this very extensive study has been negative. The truncated Lagrange and Hamilton equation have no value, to my knowledge, for the treatment, for any quantitative treatment of interior dynamical problems. Okay, this means we have to go beyond Hamiltonian mechanics. This was the signal you got to surpass 20th century theory. Otherwise, we don't do new physics. There is no possibility whatsoever I can possibly foresee. And this happened also at MIT. It was the birth of the Lie-Isotopic, of the isotopy of Lie theory, I should say. What is essentially the gist? The gist essentially was this, that I wrote the entire Hamiltonian mechanics in this abstract formulation. It's not so much abstract, but it's called unified. Unified variables and the cotangent space, or if you want, the phase space, in which you use a 2n unified symbol A, in 2 dimensions, representing coordinate and momenta. And then introduce this 2n function of the momenta with wherever with 2n, the n dimension are 0. If you do this, basically you get a Hamiltonian equation written in a synthetic form, in a unified form. Omega countervariant is the Lie tensor. The covariant version is characterized a fundamental symplectic 2 forms. And then the brackets are, those are the brackets and verify beautifully Lie theory. This is classical realization of Lie theory as the foundation of classical mechanics. What I did then, when I was at MIT, I removed the not, here. I assume an arbitrary R function in 2n dimension, and everything stays the same. Basically those things are identical, except for that the removal of that restriction. But the analytic equation derivable from a first order variational principle are now the most general possible analytic equation, namely equation derivable from a variational principle. And I discovered that those equations were first formulated by Birkhoff, and therefore I called this mechanics Birkhoffian mechanics, and I dedicated the book I named the second volume with Springer-Verlag Birkhoffian generalization of Hamiltonian mechanics. But the point that really struck my imagination was that I looked at the bracket. The brackets are the most general possible antisymmetric brackets in classical mechanics. And those brackets verify also the Lie axiom, antisymmetry and Jacobi identity. So, but this was non-trivial, ladies and gentlemen. This is non-trivial, because this is the simplest possible bracket, the Poisson bracket, and this is the most general possible one. So here you see clearly a generalization of the algebra, yet preserving the axioms. My wife, who had spent 7 years in her classical study of Greek in Italy, suggested the name isotopy from the Greek isostopos, preservation of the topology, and that's how the name was born, Lie-Isotopic, meaning it is still Lie, but not identically Lie, is broader Lie under the preservation of the axiom. This was basically the most important result that I obtained at MIT, except nice but very complex formulation. Well, before passing to the next slide, I would like to present a few recollections of my stay at MIT. First of all, it is my duty, pleasant duty, to remember Professor Francis Law, the head of the Center for Theoretical Physics at MIT at that time, during my entire presence. It is also my pleasant duty to indicate that not only in my view, but also in view of all other colleagues that were there from all over the world, Francis Law was a magnificent physicist. and a truly unbelievable human being. I think his stature, as from a human viewpoint, is I've rarely seen matched in the various university institutions all over the world. It is true what I'm saying, and I feel it. Also, to a certain regret, I have to note that the American Physical Society does not remember Francis Law the way it should. It should be remembered. He should be remembered. Anyhow, I had a very nice stay at MIT. MIT published all my papers, first as preprints and sent them around the world, and then he published them in the MIT Annals of Physics with fantastic technical, very nice environment. So I had a very pleasant stay. We were working 8-10 hours a day in my study. However, I was kind of alone in conducting this study because, to my recollection at that time, MIT had fantastic mathematicians and MIT had fantastic physicists. But to my recollection at that time, it did not have excellent mathematicians with a serious knowledge of physics and did not have excellent physicists with a serious knowledge of mathematics. So what I was doing was pretty fancy mathematics with very delicate mathematical subtleties. And I did not have a physicist that I could interact. Also, I had no contact with the mathematics department. And but also a number of colleagues, they were curious to know what Santilli working like crazy 8 or 10 hours a day for years. Writing all those papers, books, they're nice, but what's the hell of all this meaning of all this work for? Well, ladies and gentlemen, I could not tell them that my aim was to surpass Einstein and surpass quantum mechanics, because I would have been thrown out of MIT in a flash. So at that time, so I elected to be quiet, and that's why I had a fantastic stay with a very pleasant relationship with all my colleagues. I have been told that things, however, have changed since that time, and MIT is indeed open to novelty as it should be.